Hello and a very good day to everyone. Welcome to our podcast for analytical chemistry, course code SSCK1203. Before we start, let us first introduce ourselves. My name is Edzron Junis.
I am Aqiilah Thaahirah Muslim.
I am Fahmy Fadhyllah bin Janudin, and together we are from Group 12 of Faculty Chemical and Energy Engineering, University Technology, Malaysia.
To begin our podcast today, I would like to briefly mention about a case which correlates to our topic. In April 2010, an explosion on an offshore drilling rig in the Gulf of Mexico triggered the largest marine oil spill in history. 2 years after the well was sailed, investigators were required to answer a single question in court. From where did the subsequently discovered oil originate? This case is the central theme of our podcast. Today, we will examine the following points: the nature of trace materials found in petroleum, the analytical technique used to detect them, a critical comparison of those methods, the role of sample preparation in achieving reliable detection limits, and our quantitative calculation of the limit of detection. All of these points converge into our topic today, which is detection limit in petroleum analysis. Specifically, when does accuracy matters the most? Let's start with our first point. What is a petroleum?
Petroleum is primarily a very complex mixture hydrocarbon molecule. Compounds composed of hydrogen, carbon, but incorporated within this hydrocarbon matrix are non-hydrocarbon trace materials present at very low concentrations, ranging from parts per million down to parts per billion or down parts per trillion. So sulfur and nitrogen compounds are among the most constitutional about combustion. They react with oxygen and produce sulfur oxides and nitrogen oxides. These compounds are a primary anthropogenic source of atmospheric nitrogen and sulfur pollution. They are contributing to acid rain, ozone layer depletion, and chronic respiratory diseases. Within environment, sulfur compounds act as a catalyst, poisons, irreversibly degrading the performance of the catalytic processing.
So before we proceeding to direct comparison of a four methods, it is necessary to understand the principal analytical obstacle that all of them must contend with, like this. The matrix effects. In analytical chemistry, the sample matrix refers to all components of a sample other than the target analyte. For a simple aqueous sample, the matrix is relatively uncomplicated. For crude petroleum, however, the matrix consists of thousands of individual hydrocarbon species, organosulfur compounds, organometallic complexes, and dissolved inorganic salts, all present simultaneously. This compositional complexity produces two categories of interference. The first is physical interference. Crude oil is a viscous, high-density fluid. When introduced into a sample introduction system of precision analytical instrument, nebulizer, injector, or spray chamber, it can cause partial or complete blockage, resulting in unstable signal responses and irreproducible results. So the second is a chemical or spectral interference. Components of the matrix may absorb the same excitation energy as the target analyte or may produce ions with the same nominal mass-to-change ratio, thereby generating a false signal. The instrument is then unable to distinguish the analyte response from the background noise. These spectral overlap either artificially evaluates the measured concentration or suppress the true signal entirely.
Comparative evaluations of the four methods. The comparison yields three principal conclusions. First, no single method is universal applicable across all analytes classes. ICP-MS provides the most comprehensive and sensitive multi-element metal detections, achieving sub-parts per billion detections limits for transition and heavy metals. However, it is entirely unsuitable for sulfur determination in its conventional form. WDXRF under ASTM D2622 provides a reliable and commercially standardized methods for total silver quantifications, but provides no information on trace metals or the molecular compositions of the sample. GCX GCFID offers unparalleled resolutions of individual organic compounds but cannot quantify inorganic elements.
I would like to validate the previous points by demonstrating the analytical decision made during the investigation of the Deepwater Horizon oil spill, which is the case mentioned in the beginning of our podcast. On 20th of April 2010, a blowout on the Deepwater Horizon drilling rig operating at the Macondo prospect caused a discharge of an estimated 4.9 million barrels of crude oil into the Gulf of Mexico. This makes it the largest accidental marine oil spill in history. Following the sealing of the well, new surface oil slicks were observed in 2012. British Petroleum argued that these were from natural hydrocarbon seeps, which makes sense, given that the seabed of the Gulf of Mexico contains a lot of such features. Investigators employed GCGCFID to resolve the dispute. Certified samples of the synthetic drilling muds used at the Macondo site were obtained from the supply vessel that had been operational in 2010. These samples were analyzed alongside the 2012 oil slicks using the same instrument and method. The chromatographic fingerprint of the 2012 slick samples contained the specific synthetic organic compounds, which is specific of the Macondo drilling fluid, and a match which was clear and reproducible was obtained between these two samples. The investigation concluded that the oil originated from leftover hydrocarbons trapped in the sunken wreckage of the rig, and not from the seafloor. But enough about the case. Let's move on to our next point for today, which is the role of sample preparation in detection limit achievement.
GCSDCFID focuses on creating and identifying organic compounds within petroleum. The crude oil sample is first dissolved in high purity organic solvent, commonly dichloromethanes or N-hexane. The dilution ratio is carefully controlled to prevent overloading of the chromatic process columns, which could reduce separation efficiency and affect the quality of chromatogram. Soil samples containing large amount of gases or affectings and additional cleanups that is required. The deleted sample is cooled to approximately -20 degrees Celsius. At this temperature, heavy compound precipitate and can be removed through filtration. This step prevents columns cooling and help maintain good chromatographic resolution, resulting in a clear and more reliable chemical fingerprint.
Thank you everyone for the valuable insight for our topic today. Before we end our podcast today, I would once again like to emphasize the importance of accuracy in analysis, which is proven in real-world scenario, namely the Deepwater Horizon case. This case integrates all of our previous themes into a single real-world demonstration and underline the practical consequence of detection limit in petroleum analysis. The choice of method, the quality of preparation, and the meticulousness of the quantitative calculation are not just academic exercises. They are the mechanisms by which analytical chemistry produces knowledge that is actionable in the real world. We appreciate your attention and we hope this podcast has been informational.